Hello and welcome back to my 8-bit computer. As I promised in the last video, today we'll be talking about the ALU, which is implemented on this breadboard. And of course the ALU is supported by the flags. In fact, the flags are an output from the ALU, which are implemented on these chips here. And they form a sort of interface between the ALU and the control logic, which is over here. Now the computer at this moment is running the same program that we had in the very beginning of the series. Which is this program that consists of 3 subroutines, one to calculate the Fibonacci sequence, another one to calculate multiplication tables, which is actually what it's doing right now, and then a third one, which it just started to calculate exponents or power series. And so as you can imagine, this is quite a arithmetically heavy program, and so we're using the ALU quite a lot. And in fact, over here, all of these control signals from the control logic relate to the ALU. And as you can see, they're pretty busy in this program. Now, because the ALU is quite a complex part of this computer, we'll be splitting the discussion of it into 2 episodes. And in this episode, we're going to take the higher level view and understand what the different parts of the ALU are and how we can interface it and make it work correctly inside the rest of the computer. Now, we'd like our ALU to execute instructions like this one. We'd like him to take the values in 2 registers, B and C, and add them together and write the result into the C register. So, for example, if we had a value of 5 in the B register and a value of 9 in the C register, we'd like him to calculate the sum, which would be 14, and write that 14 into the C register. Another instruction we're interested in is an add with carry instruction. So, in this case, we're dealing with a 4-bit arithmetic. So supposing we wanted to add 2 8-bit numbers, we'd have to do it in 2 steps. And so we'd use the normal add instruction for the lower 4 bits of our value. And if that resulted in a carry, so if the result of that was larger than 15, then when it came to adding the higher order bits, we'd like him to add that carry as well as the 2 higher order portions of the numbers we're trying to add. So in effect, that's an addition with an extra 1. So we want to have an instruction to do that as well. So we can easily implement higher bit count arithmetic. Of course, we'd like a subtract instruction as well. So we'd like him to be able to take 2 registers. For example, B and A. They might contain the values of 9 and 5 respectively. And so we'd like him to calculate the difference, which in this case is a 4, and then write that difference back into the A register. And similarly to the add instruction, we'd like subtract with carry in this case, or in the case of subtraction, it's actually a borrow. So once again, if we were trying to subtract 2 8-bit numbers in this hypothetical 4-bit arithmetic ALU, then we'd first use a normal subtract instruction for the lower 4 bits of both values, and then we'd use a subtract with carry instruction for the higher 4 bits of the values we're subtracting. And if the lower part resulted in a carry, then, or borrow in fact, we'd like to subtract that in addition to this 5 from the values, from the value 9. And so the result would be a 3. So we'd like that subtract with carry instruction as well. Another instruction that we'd like is a compare instruction. So the compare instruction is almost the same as a subtract instruction. What we're going to do is calculate the difference between 9 and 5, but we won't write the result of that subtraction back into our C. All we'll do is just remember if it was larger or smaller or equal, and then we'll be able to subsequently use conditional jump instructions to have the program branch off in a different direction based on the comparison of 2 registers. So we need the ALU for that as well. Now, we'd obviously also like the ALU, that's the L part in ALU, to perform logical operations. So in this case, supposing we have 2 bit patterns in 2 registers, in this case A and B, we'd like the ALU to perform simple AND logic on each of the bits positions, let's say, in the 2 values. So in this case, the only common bits are in fact the last bit. So this is the only bit which is 1 in both values, and so the result would be of this AND would be a 1. Similarly, we'd like him to perform OR operations. So if we had these two values, once again, all of the bits contain a 1 in at least one of the two numbers, except for this bit, which is 0 in both, and so the result is all 1s except for this bit, which turns out to be decimal 13. Another operation is a NOT operation, so we'd like him to simply take whatever bit pattern we happens to be in a register, say the C register, and then simply flip all the bits. That's also a very important instruction. Now, I would say this is, let's say, the minimal set of instructions we'd like our ALU to be able to perform. But in addition to those, there are a few, let's say, nice-to-have instructions, which could certainly be useful if we could find some way of adding them as well to our ALU. And the first one, for example, is an exclusive OR. So we could compute an exclusive OR using a combination of OR and NOT instructions, but if we had a single instruction to do it, well, that would obviously save a lot of program space. And so in this case, we'd be performing an exclusive OR of this bit pattern and this bit pattern. And so an exclusive OR, in fact, calculates those bits which are different in both values. And so that would be the result. Another nice to have is an increase by 1 of a single register. And yes, of course, we could, use some other register and write a 1 in there and then add the two together. But if we had a single increase instruction, we'd actually save a register, because we wouldn't need to needlessly use it to store a 1, simply to add it to some other register. And similarly, we might like a decrease instruction, which is able to take the value from one register and simply subtract 1 from it. So these are the sorts of instructions. In fact, this is the list of instructions which I've implemented in my ALU. And so we're going to have a look at how we might go about building such an ALU. Now you'll remember from our previous discussion on some of the instructions we have, we also have these stack instructions. So here we have a pop instruction. And what the pop instruction does is it actually uses this special register which we have, which is the stack pointer. And it reads the value in data memory at the address pointed to by the stack pointer, and then writes that value into the A register, and additionally increases the stack pointer by 1. And so in order to perform that increase, we're also actually going to use the ALU. And you'll remember from the last video, we actually already came up with a encoding scheme for this kind of instruction. So we sort of said that was actually a load instruction into the A register, and we've defined a value of binary 000 for the A register. And then for this stack pointer, which we subsequently want to auto-increment by 1, we invented this special code, 110 in binary, or 6 in decimal, to designate that we're actually doing a load which is a pop instruction. So if you're not clear about that, have another look at the previous video, where we look at the program counter and the instruction register to see how we come to this sort of encoding. And we also have a push instruction, which does the opposite. So the push instruction takes whatever's in the B register, then takes the value which is in the stack pointer, decreases that value by 1, and then uses the resulting value, which it first of all writes back into the stack pointer, and secondly uses to point at memory. And at that location in memory, it's going to write the contents of this register. And so that too performs arithmetic on the stack pointer. In this case, it decreases the stack pointer by a value of 1. And so that too is going to have to somehow be implemented by our ALU. But again, for this instruction, we already came up with an encoding in the previous episode by considering it to be a store instruction. And we're storing into an address in memory pointed to by the stack pointer, but a stack pointer which we first decrease by a value of 1. And so again, we used that special encoding value here to designate that register of 110, which is 6 in decimal. And since we're reading the B register to write it into RAM, we encoded that with a value of 001. Now the question comes, how are we going to encode these actual ALU instructions, which we want to which will in a way be pure ALU instructions. They won't have any effect on memory. They'll simply take two register values, perform an arithmetic or a logical calculation, and write the result back in a register. So memory is not involved at all in any of the instructions. And in this case there are 8 of them. This is the minimal set of instructions we would like to implement. And then we had these 3 additional nice to have instructions. If we could somehow find a way to implement those as well, we certainly could gain advantages by doing that. So that gives us a total of 11 instructions which we need to somehow encode. And if you'll remember, we'd said that anything to do with the ALU will encode by setting the first 2 bits of our 8-bit instruction opcode to 1, 1. And that leaves us with 6 bits to encode basically everything else that we want to say about the ALU instruction. Now we'd like to encode at a minimum 8 different possible operations, and in a nice to have case 11 different operations into our instruction. And so to encode 8 values we're going to need a minimum of 3 bits, because you need 3 bits to express a number between 0 and 7, so any of a possibility of 8 values. And in fact, if we want to encode the nice to have instructions as well, we're going to need more. We're going to need 4 bits to encode just the operation. So we would have these 2 bits, we basically have them fixed to say we're dealing with an ALU, because any other combination of these 2 bits are used by all of the other instructions which don't really involve the ALU. And so for the operation we're going to need either 3 or 4 bits. And since an opcode is 8 bits long, that really leaves us only either 3, or if we implement these nice to have instructions, 2 bits to encode all of the registers that we want to designate in our instruction. And so we have 4 general purpose registers, which are register A, B, C, and D, and then we have the stack pointer and the program counter. So we're going to need at least 2 bits to designate a single register. So even if we limit ourselves to only the general purpose registers, we can't encode 2 registers in 3 bits, and we certainly can't encode 2 registers in 2 bits. And so in the case of this CPU, because we're using opcodes which are only 8 bits long, we can't really encode 2 different register values in here. And so we could either make our ALU instructions longer, make them 2 bytes wide, but that would make our control logic an awful lot more complex, because then we'd need to start dealing with varying instruction lengths. And up until now, all of our instructions have always been exactly 1 byte in length. And so the loading cycle has always been exactly the same. We've run through it a few times. We basically point the memory at the value in the program counter, and then read whatever byte is there in program memory and write it directly into the instruction register. And we're going to use that in the control logic to determine what to do. And so if suddenly we need another byte to contain the actual instruction, well then we might have to increase the size of our instruction register, or we might need a second one, or we might need the control logic to start becoming stateful, because it would have to remember the decisions it made based on the first byte of the instruction, and then take further decisions based on the second byte. So it would make the control logic an awful lot more complex. And so in my computer I've taken a simpler approach, which is to say, well, okay, this is just the way it is, so we're going to fix one of the registers. And so my ALU, in my ALU, the second register is always the B register. And so in that way I'm excluding an operation like add the C register to the D register. That's not possible with my 8-bit computer. So you always need to somehow, in your program, arrange for the byte which you want to perform arithmetic with, one of the bytes at least, to be in the B register. And then we can freely choose the other register. And so I've taken the decision to also implement these nice to have instructions. And the consequences of that is that I need 4 bits to encode the operation, and that means I only have 2 bits to encode the single register that I want my ALU to operate on, the other one being the B register. And because I'm only using 2 bits, I'm in fact limiting the ALU to the general purpose registers, A, B, C, and D. Now, for these instructions, that seems alright. You know, we can simply say that's a limitation out of our computer, is it can only perform arithmetic or logic operations on the general purpose registers, so it can't do it on the program counter or on the stack pointer. And remember, we have move instructions, so we can always perform the operation in a general register, and then if we really need it, that value in the stack pointer or in the program counter, we can always move it into one of those registers subsequently. But then you might be wondering, okay, but surely that's going to be a problem for pop and push, because they explicitly need to increase and decrease the stack pointer. Well, that's one of the reasons why we're not encoding the pop and the push instructions into the ALU address space. But instead we're using this special value here, and in fact we're encoding them as load and store instructions respectively. And so that way these instructions don't really need to fit into that scheme. So the fact that we can't directly address the stack pointer in this case, that's fine, because this instruction is not encoded using that scheme at all. It's encoded using the load and the store scheme, which we looked at in the last episode. Of course, it does mean we can only perform addition or subtraction, and we can only perform addition. In fact, we can only perform an increase or a decrease on the stack pointer. We don't support any of the other operations directly on the stack pointer. But as it turns out, that's been fine, and I've been able to write a whole lot of interesting algorithms and programs using these limitations, and it certainly is a big step forward compared to Benito's design, which basically had an addition and a subtraction without carry on the fixed registers A and B, and that was it. And so this is certainly a big improvement on that. We can freely choose one of the registers, one of the operands at least of the operation, and we have an awful lot more operations that we're going to support. So we'll live with this architecture for the moment. And so this basic structure of the ALU, so we have the two operands coming in and the result being calculated, going back into the first operand. And of course we're using some control wires here, which are going to tell the ALU which operation to perform. And so that's pretty much exactly what we'll do for all of these instructions. And these are all the instructions which take two operands, add, subtract, compare, and exclusive OR. But then of course we have a few instructions which take only one operand, not increase, decrease, even push and pop. Although we're encoding them differently, we're not using this encoding scheme, they will of course use the ALU to perform their operation, so the ALU needs to support them as well. In fact, the necessity of having a possibility of increasing or decreasing the stack pointer by 1 was one of my major motivations for enabling that same feature on all the registers, because we have to implement it anyway if we want to have a stack pointer. And so in this case we need to configure the ALU a little bit differently, so that the second operand isn't actually going to be the B register, but is going to be, let's say, a fixed value of 1, or if we're, depending on how we'll actually implement the decrease, it might be -1. The same for the NOT operation. So in fact a NOT operation is an XOR with a value of all 1s, or in 2's complement -1. So even for the NOT operation we can get away with using this structure. So what we need is some mechanism for configuring our ALU to use either the B register as its second operand or some fixed value. And that's something we're going to have to deal with in our ALU design. So here is one possibility. Since we want to be able to address one of 4 arbitrary registers, we're going to do that through the bus. And so the first operand, which in this drawing is on the bottom of the ALU, which could be any of the 4 registers, is in fact going to come in through the bus. And the second operand, as we saw, is going to be either the B register, or for some operations it's going to be a fixed value of 1 or -1. And so we have a control wire that goes into that selector. So the control logic is going to control these control wires to tell our ALU what to do. And so one of the first things it'll have to tell the ALU is whether it should take the B register or some fixed value as its second operand. And so we have a control wire for that. And then the ALU operation itself, and since we decided we were also going to implement the nice to have instructions, we're going to need 4 control wires to allow us to designate one of 11 possible operations that the ALU should perform. And then we need obviously the first operand to come in from the bus, and then we need to store the result of that calculation back into that same register. So our output also needs to be connected to the bus. But of course, this design isn't really going to work because we have two components, one of them reading and the other one writing directly to the bus. And as we saw when we talked about registers in that episode, we can't do that because if some other register, let's say we have the A register up here, is outputting its value onto the bus, well then the ALU can't be outputting a value at the same time. That's going to cause this bus to have an inconsistent state, or worse, if two components are asserting on a particular line of the bus contradictory values, one of them is asserting a 0 and the other one's asserting a 1, we're going to have a very large current flowing on that bus, and we might actually damage some of the electronics. So we can't do that in the same way that we couldn't do it for registers. So at the very minimum, we're going to need to buffer the output back onto the bus from the ALU. And so this could be one of these 74 HCT245 chips, for example, which we've been using in the rest of our computer, which is going to allow the control unit to decide when we're going to output on the bus. And so it can then make sure that if at any point the ALU is outputting onto the bus, well then none of the other registers should be outputting onto the bus. But even this design isn't really going to work, because supposing that we wanted to add the A register and the B register together. So the B register is going to come from the selector. The control logic will know that it should activate the B register, so that will go into there, no problem. And the A register will be outputting its value onto the bus, and that buffer will be disabled. Control logic will have set everything for that to be the case. So the A register is outputting its value, and so that's going to flow into here, and okay, fine so far. Then these control wires will be set in some particular combination by the control logic, which will tell the ALU to perform an addition operation, and it will perform the addition, and so the result of that addition will be on these wires. But then for that value to go back into the A register needs to stop outputting its value onto the bus. And the problem is that as soon as the A register stops outputting its value on the bus, these lines will either be not connected at all, they'll be floating, or if we in fact naively enable this buffer at the same time, we're basically going to create a loop. Because there's no sort of latching in this ALU. This ALU takes wires. The ALU consists of a simple circuit of logic gates. It doesn't latch anything. So we have input wires coming in here. It's pure combinational logic, and the result goes out onto those wires. And it's doing that permanently. It's hardwired. Well, more or less hardwired that way. And so if we disable the A register's output onto the bus, then those input wires won't contain any sort of valid state anymore, and therefore nor will the output wires. And so even if we enable the bus at that point, we'll be outputting total nonsense onto the bus. We won't have remembered what that was. This component doesn't remember, it doesn't have any sort of memory. It's purely combinational logic. And so we're sort of realizing that we need some sort of mechanism to store the result of the operation before we output it back onto the bus. So what we really need is an extra register. And so what's going to happen in this case is in the same example, supposing we want to add the A register and the B register together, the A register will be told by the control logic to output its value onto the bus, and so that will flow into one of the inputs of our ALU. The control logic will at the same time tell the ALU to select the B register as its second input, and it will then set some value on these control wires to tell the ALU to perform an addition. It'll perform that addition because of its internal combinational logic, and that result will be on these wires. And so then the control logic is going to tell this register to actually latch that value, to perform a write into that register, not from the bus, but from the output of the ALU. And it's going to do that while the A register up here is still asserting its contents onto the bus to make sure that that ALU is in a valid state and adding two well-known values, in this case A and B, and therefore that the result of this addition is a well-known value, and that will get latched into that register on in one step. So it'll assert this signal as well as a write into that register. And then in the next step, what will happen is the control logic. Once the result of the addition has been latched into this register, the control logic can tell the A register to stop outputting its value onto the bus. And it can tell this register to no longer write. So it has the result of the sum latched inside itself. So it doesn't need to write anymore. But it should then write its value out onto the bus, now that the bus is no longer being occupied by the A register. And so then the result of the calculation will be output onto the bus. And then the A register could be configured to write, or some other register could be configured to take that value from the bus and latch it. And so we see that because we are using the bus for both the input into the ALU and also the output from the ALU, we actually need two micro clock ticks to perform an ALU operation. And in the first one, the first operand will be on the bus, and on the second clock cycle, the result of the calculation will be out on the bus. And that's really the only way to do it, by using a single bus, as we have in our computer. Now, in addition to providing the result of the calculation, which is then latched into this register, the ALU is also going to provide a series of flags. And the flags are things like the carry flag or the zero flag, or they're going to give us some extra information about the calculation, or in fact about the value, which is here. And in our computer we have 4 different flags. And the zero flag, for example, simply says if all the bits of this result are 0. And that allows us, for example, to compare equality. So if we perform a subtraction of 2 values and the result is 0, that means the 2 values were equal. So that's a very useful flag which the ALU can provide. Also the carry flag. So if we're performing an addition, for example, let's say we're cycling through all memory addresses, and so we're using the increase instruction. And so our second operand might be a 1 instead of the B register. So we keep increasing a register by 1, by 1, by 1. So we cycle through all the numbers. And at some point we'll arrive at 255. And then when we add another 1 to that 255, well, it's going to cycle back to 0 again, because we only have 8 bits. And when that happens, the ALU will set the carry flag. Because if we were performing a 16-bit addition, then we'd need to carry the result of that addition into the higher order 8-bit byte. But we can also use that carry flag in control logic. In our program, we can jump based on a carry. And we've seen a few examples of that in previous episodes, where our program will simply cycle through all possible addresses, and then when it's reached the last one, it'll halt. And we've typically done that using a jump on carry instruction. And so that carry flag will come out of the ALU for any kind of operation. And for the same reason that we need to latch this value, the result of the calculation, we also need to latch the flags. Because the carry flag might be permanently set, but for example, the 0 flag is going to really reflect the state of these 8 wires. And those 8 wires are going to change as soon as we change these operands. Once again, this is purely combinational logic in here. There's no notion of latching. And so we need an extra register, which in this case is only 4 bits long, which is going to contain all of our 4 flags. And so whenever the control logic tells our ALU register that it should latch the result of a calculation, it's also going to latch the flags at the same time. Now the biggest difference is that these flags, the value of these flags, of course don't go to the bus, because they're going to be used by the control logic itself to make decisions. And so in fact the output of that flags register, there's no control wire to enable or disable output onto the bus, because those flags never go onto the bus, they go directly into the control logic, as we'll see when we discuss the control logic. So here is a view of that ALU in the hardware, and we can start recognizing some of the components. So the register, which is going to the control logic periodically tells the ALU to write the result of its computation in, is being shown on these LEDs, and the actual register chip is here, and that's the 74HCT377, which we know very well and have been using quite often in this computer. And so the inputs to that chip come directly from the ALU, from the calculation unit. And its outputs are going on these green wires here to a buffer chip, and that's the famous 74HCT245, which we're also very familiar with, and that is outputting its contents back onto the bus. And the input to the ALU, of course the first input also comes from the bus, and so these blue wires, which represent the bus, which this buffer sometimes outputs to, are also connected to, and we'll see later how that works, all of the inputs of the real ALU, and the ALU is split over a number of chips, over here and over here. And now the control logic, so as we saw, it has 4 input lines to designate the actual type of operation, and so for the moment we'll just take it on faith that those are called ALC, ALS0, ALS1 and ALS2. Those are the 4 input lines which determine which operation the actual ALU should perform, and we'll have a look at exactly how that's organized in the next episode. But so for now we'll just accept that those 4 lines go to the calculation unit and simply tell it what to do with its 2 operands. And the result of its calculation, based on these 4 lines, is then latched into this register whenever the control logic tells the ALU to write to the ALU register. So here we have the write and the enable signals for this register. And then finally, we have the flags over here in the corner, and so they too have a register chip, which is in fact a 74HCT173, which is a 4-bit register, because we only have 4 flags. And so that too will be written whenever it's being told to do so by the control unit. And as you can see right now, the ALU is about to perform an operation, because the ALU write signal here is being asserted. So these register chips for both the flags and the ALU result will latch the result of some computation as soon as the next rising clock edge arrives. And in fact what's happening is at this moment the computer is executing this pop instruction. So it's popping into the D register. So what does that mean? Well, it means that the stack pointer, which is over here, and for those of you who are fast at binary decoding, and that's showing a value of 253 right now. So that stack pointer is pointing at memory, at a certain address in memory, and whatever is at that address in memory will be written into the D register, but the contents of this value 253 will also be increased by 1, and the result of that will be written back into the stack pointer. And so that's the operation we're most interested in right now, because that's going to use the ALU. Now finally, remember that the second operand is either the B register or a hard-coded value, which so far we've called 1 or -1. And so we have a final signal from the CPU, from the control logic here, which is this ALU B signal. And so that tells the ALU whether it should use the B register or its hard-coded value to perform the calculation. And now in this case, in the case of the pop instruction, we simply want to increase the stack pointer by 1. We don't want to increase it by the value of the B register. So for this particular operation, that control signal is not being asserted. And so the first input into the ALU is coming from the bus, and in fact the bus right now contains the value of the stack pointer, because the stack pointer register is being told to enable its contents onto the bus. And so they're going from the bus into the first operand of the ALU. And the second operand of the ALU, because of this signal, this selector which we've built in here somewhere, isn't actually selecting the B register, but it's selecting the hard-coded value of 1. And so these 4 lines are going to tell the ALU to add 1, but not the B register, to the value which is in the stack pointer, which is in fact also on the bus right now. And so on the next rising clock edge, it should write the result of that calculation into this register, and that should be 254, because 253 plus 1 is 254. So if I advance the clock, then there we have 254, and so that was one example of an ALU operation. But as we saw, we actually need 2 cycles, because that value is now inside this register, and only now are we able to write this 254 out onto the bus. And we're doing that using this ALU enable signal. So the output of that register is now going through this buffer chip which has been enabled onto the bus, and so the stack pointer will actually take the result of that calculation and latch it inside the actual stack pointer register. And there it is. And so at the same time, it's also gone and read no, it's actually going to do that now, read the value of the D register, which you can't see right now. And that's going, the memory contents are going to be written into that D register. And so that's one example of an ALU operation. And the next instruction is increase the D register. And so this is very similar, the work that the ALU will do is very similar to what happened in the last instruction. In this pop instruction, it was in fact the stack pointer which was being increased. And now the value of the D register is going to be increased. So in fact, the D register is on the bus right now, and it's asserting a value of 6, which you can't see right now, but we'll see it soon enough. And at the same time, the ALU, once again, is being told through these 4 signals, ALC, ALS 0, 1, and 2, that it's going to perform an addition. And this B signal at the moment is not on, so it's not going to take the second operand from the B register, it's going to take a fixed value of 1, because we're performing an increase instruction. And once again, the result of that calculation is going to be latched into this special register that we have for the ALU. And so on the next rising clock edge, we should see a value of 7, because the bus is asserting a 6 right now, written into that register. And so there's the 7, which is 3 1s in binary. And so on the last part of the instruction, that value is now being output from that register through this buffer onto the bus. And then the D register is going to write that inside of itself, because it's going to enable its write signal. And so that will be the conclusion of this increase D register instruction. So now we're about to execute this AND instruction. And so here we're going to take an AND, this is a bitwise AND, of the contents of the D register and the contents of the B register. And we're going to write the result in the D register. Now you can't see it right now, but the D register contains that value of 7, which we calculated a moment ago. So that's, in binary, that's 5 zeros and 3 1s. And the B register contains a value of 15, so that's 4 zeros and 4 1s. So the result of the AND operation should in fact be the same, should be 5 zeros and 3 1s, because the 4th bit of that sequence is not set on the D register, and so the result of the AND should in fact be the same value that's already there. And so for this operation, we can see that these first 4 bits, which send the actual operation code to the ALU, are different. They are 0, 0, 1, 1 right now. But the interesting part is, for this instruction, we're telling the ALU that its second operand should come from the B register. And in fact, if you look very closely, you'll see 4 green wires here moving up from the ALU. And here are the last 4, so that's 8 wires in total. And they're actually hooked up to the B register. So the output of the B register is always available for the ALU. So that's not coming to the ALU through the bus, that's directly wired to the ALU. But of course the other operand is the D register, and that's coming in through the bus. And so that contains a value of 7 right now, and on these B wires we are having a value of 15, and so the ALU is then going to perform this AND operation on those 2 bits, and so the result once again will be latched into this register, because we're telling that register that we would like the output of the ALU to be written. And so that's what will happen on the next rising clock edge. And then once again, that value, which as we said would remain 7, is now being output back onto the bus, and that's going back into the D register. Now the computer is in fact about to execute this add instruction as a final example. So it's going to add once again the B register, and this time to the C register, and write the result in the C register. And at this moment the C register contains a value of 28 and the B register contains a value of 7. So that 28 is being output onto the bus and is coming into the ALU along these wires and is going into the first operand. And so the control logic is once again giving this 4-bit signal to the ALU, which in this case means an add. But for this add, it's actually going to take the contents of the B register, so it's not an increase or a stack instruction. We really want that 7 to be added to the 28, which is on the bus right now. And so we're telling the ALU that it should take the contents from the B register on these wires and add them together to what's coming in on the bus, which is 28. And then it should latch that into this register, which we have. And so on the next rising clock edge, this ALU register should contain the value 35, because 28 plus 7 is 35. And so if you're any good at binary calculations, this is 32 plus 2 plus 1, that's 35. And so that 35 is now going out onto the bus, because that ALU register is being instructed to enable its contents onto the bus, and at the same time it's going to be written back into the C register, because that's what this add instruction is going to do. It's going to add the value of which was there, which is 28, to the 7, which is in the B register, and the result will be 35. So that's a first look at the way we've implemented the ALU. So we've seen what instructions we want to support. So we have arithmetic instructions, add and subtract, both with or without taking into account the carry. We have, of course, all of the logical instructions, the and, or, not, and the exclusive or. And then we have 2 single operand instructions, increase and decrease. And we can use those for any of the 4 general purpose registers, but we can also use it on the stack when we're implementing the pop and the push instructions. And so the control logic has several signals with which it controls the ALU, and so 4 of those are going to determine the actual operation to be performed. We have another signal which tells the ALU what its second operand should be. First operand is always the contents of the bus, and so sometimes the second operand will be the actual contents of the B register, which come in through these green wires, and sometimes the contents will be a hard-coded value. And then we have a register which we can use to latch the result of the calculation, and the main reason for that is we can't output the contents of the calculation directly back onto the bus while we are still reading in one of the operands from the bus, and so we have a latch, let's say, on the way. And so it's a 2-step process whereby we first write into that register and then we read from it. And so at any time when we write operation of a calculation into that register, we also set these flags. So that's a 0, a carry, an overflow, and a negative flag. And those are also set by, let's say, the condition and the state of the calculation at the same time when we write the actual contents, the actual result of the operation. And so in the next episode, we're going to have a closer look at the actual arithmetic and logic operations, now that we understand where the inputs come from and what we do with them once the calculation has been performed. And so the only thing that we still need to look at is to understand how these 4 control bits actually perform the arithmetic or the logic operations that we then subsequently store into this register. And so we'll have a look at that in the next episode. See you then.